Alex,
Hey.
did you get pictures? I just sent it to you.
Yes, I did. Thank you.
Alex, do you get the pictures?
Yeah, I did.
Okay, good.
Can you actually email them? It lowers the quality when you text them.
Okay.
Okay, so let's get started. 1,3-azoles. These are some of the centerpieces of modern medicinal chemistry. And let's see, Zoe is anywhere? Nowhere to be found. Okay. Ziki. Yeah, all right. Well, you're going to help us a lot today. You're, I guess, the sole remaining member of the azole team. So the way the lecture is structured today is heavy on the case studies. There are hundreds of variations of the ways that you might make imidazoles, oxisols, and thiazoles. And so it's really hard to encapsulate in 90 minutes all of them. So what I tried to give here is a set of guidelines that help you think about the strategy. And then we'll go through a number of case studies in the variety of contexts that are even exhibiting the benzo-fused derivatives, which in past years we haven't covered. It can get kind of hairy, but I think you can handle it based on everything we've talked about so far. The other thing that's good to keep in mind is the various oxidation states that are somewhat fluid in the oxidation direction. So if you look at a thiazole, imidazole, oxisol, and remember that the azoline is the fully reduced one, the azolidine is a further oxidized one, and then if you fully oxidize it, you get to an azole. Remember that in the case of the benzandulated or the regular monomeric ones, often if you get to any of these oxidation states, getting to the final one is pretty easy to do. So keep that in mind when you're thinking about these. Okay, so the standard ways of putting these together that date back 100 years really stems from this main retrosynthetic depiction shown here. And probably the oldest way of making these are the first two that I'll cover. On the top left here, the Robinson-Gabriel to make oxisols is probably the first way to make an oxisol, and it's kind of intuitive. So you've got essentially a 1,4-dicarbonyl, but there's an as-a-bridge in there, and when you lose water, it's kind of like you just made a furan, but an as-a-furan, which I guess you would call an oxisol. Same thing, thiophene, pyrrole. Do you remember? I mean, it looks if you just pretend this nitrogen is not there, it's all the same as furan. And issues, problem, mistake?
Just azoline and azolidine are reversed.
Oh, is that right?
Azolidine is the fully reduced,
Oh,
like
yeah.
pyrrolidine.
Yeah, you're right. let's switch these. So, thanks. Great. Okay, so if you recall, thiophene, furan, pyrrole synthesis, and just imagine there's an as a bridge in there. The Robinson-Gabriel is essentially the same as the 1,4-dicarbonyl that you learned before. Okay, the next most popular one is the Hansch. And the problem people have with the Hansch is often stemming from concerns about regioselectivity. So we'll cover that in depth today with a number of case studies. But it usually involves a ketone with Y equal to a leaving group, and sometimes the leaving group can even be a hydroxy, as you'll see in a moment. So leaving group can be rather fluid. Usually, though, it's a chloro or bromo or a tosyloxy. And you then merge that with some sort of either amidine or thio derivative to either make the imidazole, the thiazole, or if it's just some sort of amide, you're going to make the oxisol. If Y is equal to NH2, that goes by the name of Markwald. And Markwald can be accomplished by using some sort of isocyanate or carbodiamide or isothiocyanate to make either of the classes of a 1,3-azole. So, for example, if you take an alpha amino ketone and you react it with an isothiocyanate, you get out that imidazolone. And that sulfur can be easily removed to give you the free imidazole, or you can treat it with something like POCl3 and start adding in various nucleophiles. Okay, so yeah, via zolidines. So if you take your alpha amino halogen substituted system and you treat that with an aldehyde, you're going to get, of course, bless you, a reduced form of the azole, which can easily be oxidized with whatever you like. We've covered so many already. Palladium on carbon, no hydrogen, DDQ. Sometimes air is enough to accomplish it. One of the most useful ways of making all of these systems is the Van Leusen. The only restriction on Van Leusen is that R1 always needs to be hydrogen because, of course, you're dealing with isocyanide. And that's going to require that there's no substitution at carbon at R1. But as a result, you can modularly make a number of very intricately fused imidazoles. We'll see a couple of examples of that today. And we'll see Van Leusen at least 3 times today. Super useful way of making imidazoles, oxisols. Okay, so any questions on the general ways of making azole systems before we get into the case studies? Okay, so back in the heyday of CombiChem, everybody was obsessed with putting things on solid phase. And Merck, in a very interesting JOC paper many years ago, reported this interesting transformation that encompasses problem of the day number 1. So maybe Ziki, as the captain of the azole team, can help us out with that. We can either pass the iPad to her, or she can just tell me where to put the chalk. So EDC, or a general dehydrating agent.
EDC first activate the acid.
Okay.
And then the oxygen on the amide would polymerize and then attack the carbon on activated acid and the amide.
Okay, give me a second to draw what you just said.
Now you can get this sort of like
This is a super acidic position. So it's probably going to look like that. And now what do I do?
And this reacts with the
Okay. Is that right?
Yeah, and then this loses carbon dioxide.
And then aromatized lose a toss of work. And we have an imidazole. Super useful for CombiChem. But strangely, the authors note that this reaction doesn't work in solution. But they use this to, if you look at the NMRs, they're like right off, as soon as you cleave it off the resin, it's super clean. I mean, I suppose you could find a way to get this to work in solution, but it looks like an ideal CombiChem-like process, so why not just keep it on solid phase? And indeed, they use this to make dozens, if not hundreds, of variously substituted imidazoles. And since we're on the topic of imidazoles, it kind of makes sense to go through the very first way people make imidazoles, which is a Debus name reaction. And it involves taking a diketone and using ammonia, heat, and an aldehyde. And out pops an imidazole. Presumably, this goes via the intermediacy of the diimine you also make that one in the soup, and you can imagine that then cyclizes after addition. Thermodynamically driven process. And obviously this method is best used when your diketone is symmetrical. Unless, if it's just ammonia, it doesn't matter. But if you're using, in the case of a compound like this, where you're using an additional amine, then it kind of matters. So, for example, these Pgp mediators were made using the same exact process. Now, the trick here is we're going to have Ar diketone plus ammonia, or surrogate thereof, plus Ar CHO plus hexylamine. Now, you may say, Phil, this makes no sense. Because how do they control the formation of the substituted imidazole versus the unsubstituted imidazole? And the answer to that is they use 20-fold excess of the amine relative to ammonia. For MedChem, this is fine. You guys make imidazoles over at Pfizer? Substitute them.
Yeah.
All right. So to review, if you have the dicarbonyl and these two are the same, or if they're different and you're just using ammonia, it doesn't matter. But if you're using an amine donor and an ammonia, obviously it matters if AR and AR prime are different. You can get regio control if there's some dramatic, if you get lucky, basically. But usually you'll get a mixture of the two, which for MedChem could be fine. And I still see this type of process used even today. Diketones are easy to get your hands on through a variety of different ways, from the alkyne, from the olefin, from the ketone itself. So they're pretty good starting materials. Questions? Anybody need caffeine? Okay. All right, let's take a look at iprosartan. And this is a story. These type of imidazoles have captivated medicinal chemists, some at the highest levels at DuPont and Merck for over 30 years. Some of the biggest names in MedChem that you know as legends in the field worked on these types of imidazoles for a while. So this next segment covers the careers of hundreds of people. Okay, so let's think about a simple imidazole like that from the standpoint of a medicinal chemist. And we would like to get, obviously, some diversity here. So, Max, what would be a logical way to make a library of that kind of compound?
I mean, I kind of want to do inoculation, but...
Yeah, why don't you want to do that?
Well, you have to use like Semtric probably, right, to sterilize.
Semtric didn't exist back then. But there was a different trick that existed in order to force the alkylation to take place at that distal nitrogen relative to the CH bond. Does anybody remember what that is? We covered it in lecture 2, I think. Yes, brilliant. So you can alkylate that. It only goes away from the chloro, and then you can remove it with the palladium on carbon.
Is it easy to do?
I'm sorry, Nick, can't hear you.
Is it easy to do chlorination
It is not not difficult at all. Yeah, just NCS will give it to you, no problem. And that's exactly what they did. So then how do we make this? Well, this comes from pretty easy starting material. Dihydroxyacetone, your amidine, and cook them up. And you can even use ammonia to make the process even cleaner. That happens at 60 degrees. Following that, you do a chlorination. Straightforward, because you do have, after all, Nick, you do have a pyrrole nitrogen here. So imidazoles can be both. And there's a chapter in the book on imidazoles where we cover substitution and covers the various ways of doing electrophilic aromatic substitution on imidazoles. So you can do that. Okay, the process chemists were obviously not interested in doing an alkylation event. So we need a completely different way to put this together. So the process chemists know what target they have. They don't need any diversity at all. So it stands to reason that one of the components we're going to want to use for process chemistry is simply this one. Correct? Now we need an electrophile, which will give us some measure of control in the addition step. Imagine an addition, and then a cyclization, a loss of HBr, and that will give you the wrong Ricci chemistry. So what's amazing about this transformation is that the selectivity is complete for the more electron-rich nitrogen atom adding in. So it is this nitrogen that takes over and adds in directly, not that process. This can be confusing because you may say, oh, well, sterically, shouldn't be NH2 add in? Do we have that backwards? Yeah, we do. Sorry. So the selectivity is remarkable because you might expect, from an electronic standpoint, that the benzyl group would give you a higher selectivity. And we'll see an example of the opposite in a little while. But what they noticed in an empirical sense in the process scale was that they got complete selectivity for the free amine adding in in the beta position, followed by loss of methanol, and then cyclization, and loss of HBr. Sorry about that. That's confusing. No questions on this?
So which one is this? So the more electron-rich one. Which is the electron-
This is a sterically guided process, so this nitrogen attacks here,
Okay.
as drawn initially, as you would intuitively predict. We'll do this 2 more times. Yeah, what do you say, Sarah?
Sorry, is the alcohol substitution, is that becoming the aldehyde in the product?
The aldehyde is in the product, yes.
But, is that getting oxidized?
For this one, you get the alcohol as a product.
Oh, is it on the wrong carbon?
I don't think so. So, if we draw the arrows, after the Michael addition takes
Oh,
place,
sorry, in the medchem route.
in the medchem route, you get selective alkylation away from the chlorine.
Oh, sorry, I just mean the alcohol substitution. Like the methane and the...
Oh, I can draw the NH either spot.
Oh, okay.
So just, yeah, I drew the other tautomer, but if that's confusing,
Oh, okay.
this is the same. You can put the proton either way. Yeah, good question. Okay, so you might imagine instead of an aldehyde going into an aldehyde, they probably explored other substituents here. So another substituent you could look at would be probability number 2, which asks the question, if you've got the exact same electrophile, but this time you use a nitrile instead of an aldehyde, what happens and what might be the sort of drama event in process scale for this? So probability number 2, hopefully Tucker can help us out with.
Let's hope so. I'm guessing we're going to start off with the...
Oh, you don't want to use the iPad, okay. NHR.
Guess not.
All right, so you just have to tell me what to do.
Yeah. Amidine. Nitrogen. Would attack 1,4.
Can you switch back to the big screen?
Okay. And I guess something's going to happen to go one way versus another way, because we get 2 products.
Well, you can have addition into the cyano instead of displacement.
Would that give us our imidazole?
It would give you... Diazonium.
Would give us something like this, which would then there we go. Doesn't look like imidazole.
No.
That's your minor product. Minor enough that the process chemist couldn't use this route. The major product, of course, is designer. Okay, so we need two different routes now for losartan, which is just an analog of this first one we saw. These are two different process routes that people use. And when you think about this type of molecule and the OH here, you might immediately imagine that this could arise from a species like that. Now, is that a signaling element for anything we've seen before?
Exactly what it's.
Can't hear you, Max.
It's kind of exactly what we've seen before.
Is it exactly what we've seen before?
It's not the same compound, we just drew.
How do we make that compound without doing all the chlorination stuff?
Use Vilsmeyer?
So Vilsmeyer would require and making this, how do we make that thing?
So you break the lower CN.
Sorry, Nick, what do you do?
You break the, you disconnect with the CN bond.
Got a lot of CN bonds. This one?
Yeah.
Any other ones?
And the one next to this CO.
Looks like we can just take glycine, heat it up with butyl nitrile and get out the product. Yeah, the other way of doing this is what Max said, the classical approach, which would involve making this from dihydroxyacetone, followed by chlorination. But the Lanza improvement of this DuPont route was to simply use Vilsmeyer to get the exact same product.
Yeah, so it was the other CN bond, the one next to.
You can do the other one too. So if you prefer, that will also work. How do you make that, Nick? The amino ether?
Take the acid.
Well, you don't need to take the acid. You already got this stuff sitting around. So remember, nitriles, super useful precursors to everything you're going to need. We're going to see this again and again throughout the last few lectures we have. So maybe it's worthwhile to take over some space somewhere and remind you of all the cool things you can make from a nitrile. I mean, this will probably help you in the test. So if you treat with dry HCl, you get out the chloro. If you treat it with hydrazine, you get out that. If you treat it with hydroxylamine, you get that. If you treat it with methanol, you get the imino ether. And if you treat the imino ether with H2S, it'll give you that. Are there other ones I'm missing? I think those are the most useful ones that we'll see. But remember, nitriles are great precursors to all the things you might want that look like that. Almost everything you need that looks like that can come from a nitrile. And this is all process chemistry, so it's not just sort of low-yielding med chem stuff. Questions? Okay, cool. You know, Merck is not done with this problem, and there was even a paper a few years ago from Merck in Orglet where they present yet another way of making these types of imidazoles. But first, before we get to this problem today, how do you make these? Zane, you got a real quick one-step route to get that? Or I'll give you 2 steps. What is this a signaling element for? Sorry? Vince? Sorry? Strecker sounds good, Hannah. So we can take an aldehyde, any aldehyde on the planet, strecker with ammonia and cyanide, and now we have a great precursor that you can acylate, and then you can treat it with problem of the day number 2 or 3. So who's good with phosphorus? Oh yeah, Dongmin's going to help us. That's great. Super. This should be easy for Dongmin.
Can I just talk through?
Oh, okay, sure. Nobody likes the iPad. Okay. What do we do?
Yeah, so first you have the trichinophosphate attacking the carbon tetrachloride, attacking the chlorine, the carbon tetrachloride, and generate a chlorophosphomate species, and CCO3 minus. And then you can have the amide oxygen attacking the chlorophosphomate species, which gives you the
Okay, now what do I do?
and then I can have the chloride attacking the and the nitrogen in turn attacks the imine and take out phosphorus dioxide.
That's the mechanism I like best. If you actually read the paper, they propose by NMR studies, they propose a 7-member ring intermediate that gives the same product. Which then collapses to that. But what Dongmin wrote is definitely intuitive, and they, of course, thought the same thing. Then they looked at NMR, and they did careful studies, and they found that actually they're making these 7-member ring intermediates that then collapse over time to the product. So think about the utility of this. This is pretty useful, because you can take any aldehyde on the planet, quickly make the strecker, acylate it with any kind of acid you want, then just treat it with simple apple-type conditions, and you get out a chloroimidazole, which can be taken further to Suzuki coupling. So now we have 1, 2, 3 substitute of the imidazoles very quickly. And if you want to alkylate, we know the chloro effect is going to direct here. So you can make fully substituted the imidazoles in like 2, 3 steps. Very useful. Okay, there's some other useful recent imidazole syntheses that have come out that I find myself using quite a bit in consulting. One of these is from BMS. And what's intriguing about the substitution pattern is you've got this nitrogen that's got something that you can't really alkylate. So in this paper, they showed you could put T-butyl, adamantane, whatever, aryl, anything you want here, and you just plug and play. And so the beauty of this approach is it cuts here and here to give you complete reach of selectivity. So you treat this with DMF DMA and pyrrolidine, and it gives you this intermediate. Which then the amine adds in here and there. And this can be done on process scale or medchem. How about this strange one? I'm pretty sure most of you would make an initial bond disconnection that's not what they did. So let's just discuss that for a minute. What's the first intuitive disconnection that you think you might make here, Steve?
From the JFC paper?
Mm-hmm.
I guess I would cut the carbon-carbon double bond between get to 1.5 barrel and another.
This one here?
Yeah.
And then you want to recapitulate that.
Ketone and
This amine?
let's make up the
This?
sure.
Okay. And react with what?
Maybe that's not the best one.
Well, I was thinking someone would say that. If we take Steve's logic, I mean, I think what you probably want is you're thinking something like that. Do some sort of reductive emanation followed by cyclization. It's reasonable.
Why not a Van Lucen disconnection here?
Sorry, what do you say, Saul?
Why not a Van Lucen disconnection here?
That's a great question. Why not a Van Lucen? So if we do Van Lucen, tell me the components you need.
Aryl isocyanide. Like a alpha something pyrrolidine.
How about just that?
Sure.
That works. They take pyrrolidine, mild oxidation. I think they use iodosabenzene. They get the imine in situ. They take the imine in situ, react it under Van Lucen conditions with base. Now pops the product. It's pretty quick. You might say, hey, Phil, why can't you use Van Lucen to make that? It's a little trick. You might be able to. It's a little trickier, though, when you've got a carboxy here. If this were aryl or alkyl or almost anything else, you could use a Van Lucen again. Remember, if you're looking at a imidazole from a strategic perspective, and you have a free C2 position, it's just CH there, the thing I would always think about in your wheelhouse would be Van Lucen. Think about that first, just really quick, because often you can use imine and very quickly stitch together all sorts of imidazoles just by thinking about what the imine precursor would be. Van Lucen super useful, both medchem and process. Okay, if you're not traumatized already by radio labeling from the exam, here's another one for you. So we need to label this interesting intermediate that has in it a pyrimidinone and an imidazole, and we need to get C14 right there at that position. That's an annoying position to have it. Presumably they need it there, maybe because of some sort of metabolism that takes place here. Well, we've got a bicyclic system. We've got some limitations on our starting material. And so we can take...
If you disconnect ring A, you get to an amino-imidazole, which looks a lot like a nitrile. I haven't thought this through yet, but I feel like that nitrile is going to be used.
you don't need to think it through. We're just looking for someone to say something. This is what you want?
Sure.
Okay. Let's remember we have And you said something very interesting before. You said, this aminoimidazole looks like it's a nitrile. So pretty much you don't have to say anything more. I'm just going to use what you said in that one sentence, if that's okay. That's what Sol's one sentence leads to. That's just a commercially available glycine derivative. So we add that in, and then treat with base, get out the product. And why is this so useful? Well, because it traces back, as Sol noticed in his one-sentence solution, to this. So we can take cyanamide, treat with trimethyl orthoformate, get that intermediate imine, which can then be easily condensed with a glycine derivative, treat with base, and out pops this. And then, we need a way to make that pyrimidinone. Hopefully yesterday's lecture won't leave us stranded. So we need a component that will allow us to stitch on that piece. You can just draw that piece. Let's just copy and paste. So when we disconnect, you get that, and then you get this. Something has to be here, so let's just put this. Also commercial. Dump and stir and heat. Could you go the other way? That is, could you take a ring system like A and then build on B? You could, but that would require some sort of labeled malonate. What would you rather use, labeled malonate or labeled cyanide? Obviously, the cyanide is going to be a lot cheaper than the malonate. Cool. Any questions? That completes our deep dive into imidazoles. So the next part of the board is going to be all about oxisols. Okay, so oxisols, here's an example of how you would put one together. You take halofordanol, which is on the front page of your handout, somewhere. There it is. That's your final structure of halofordanol. And the first thing we're going to do is treat this with dry HCl. And look, we already gave the answer around here. We already know this is your translation for all things nitrile. So Tanner, what happens when we treat this thing with dry HCl and SOCl2? Remember, we have the SOCl2 in there too. There's your clue.
Sorry, I can't see.
Maybe we can put the chalkboard on the screen there. So cyanohydrin treated with dry HCl and SOCl2 in ether. Okay, let's do that. And then?
Cl acid, Cl minus acid.
Perfect. Great. You go through the intermediate shown here. It then closes. And the oxidation state you need to make your oxisol, that's hiding right there. How about VX497? Can we use anything from the retrosynthetic diagram here? Ziki, any thoughts?
For the plain oxidol, maybe use the aldehyde and cyanamol.
The Van Leusen.
Yeah.
Brilliant. So Ziki has astutely noticed we've got a nice open C2 bond. There's just a CH there. And so plus Tajmic. We learned all about Tajmic. We even learned how to radio label Tajmic before the midterm. Super. How about this VEGF, just in time for Saul's favorite topic, kinases. So this VEGF inhibitor, a kinase compound from GSK. And we need two routes. Maybe first one that would give us a rapid diversification of the aryl side chain with the amine. That intuitively would lead you to what, Vince?
Get the amino oxisol.
Okay, let's draw that out.
Looks like that could arise from urea and aldehyde.
Urea and an aldehyde.
Like that, or like a.
Something like that, perhaps? I think that might be problematic. So there's a couple of issues. I think the easiest way to make that is probably going to be via this. Wouldn't you say, Vince? Problem with this one is I'm probably, when I cyclize, just going to get an imidazole with an S-methyl there. So this is probably not going to work. Now, Patrick, do you think amino oxisols are good for libraries of Buchwald-Hartwig reactions? I mean, you can use them. You try Xanthos, but they're kind of crappy nucleophiles. But luckily, Vince has already guided us to this one, which is a much better precursor. We can take libraries of anilines and dump them in here. Yes? And this can be very easily made from that, which just comes from CS2, super cheap. It's smelly, but cheap. That will give you that. POCl3 will give you the chloride. And then adding in your... will give you that. There's another way to put these together.
Carbon disulfide, why do you get selectivity for the thioxazole instead of the hydroxythiazole? See what I'm saying?
Yeah. So the other, you can imagine the other possible product out of this would be yeah. So the question is, why does that cyclize in such a way that you get instead this enol form attacking here and losing H2S versus adding in water? And the best answer I can give you here is that it's a much better, the enol form is a much better nucleophile, and it's driven towards the oxazole formation versus the reversible adduct you get with CS2, adding in to give the thiazole. Now, when we fast forward, when we go to the, since Saul mentioned it, we can save time later, the Koch-Heilbronn thiazole synthesis is a case where the CS2 will add in. But in that case, you've got an electrophile just sitting there that has no nucleophilic properties. So if you want to make a thiazole with CS2, you have to use some innate electrophile that can't add in. So that's great, Saul, because now we don't have to cover that when we get to that part of the board. Great question. Any other questions? Another sneaky way to make these is a Saudinger. And so when you mix those two with triphenylphosphine, the intermediate you get is that, which can then isomerize to the oxazole. You see this one used a lot. Alpha-zetoketone is pretty easy to make. And the corresponding isothiocinates, also very easy to access. And so you can imagine making a parallel library of oxazoles this way. How about JTE 522? This one is tricky because of regiochemistry. Notice we haven't used any Suzuki couplings yet. And I don't think we're going to do, maybe we'll just do one cross coupling today. That's it. This is not one of them. What do you think, Cheng?
I think maybe you can use Van Olsen.
You think you want to use what?
Van Olsen? Because I guess once you get the...
Van Lucen and then CH methylation?
No. You can treat with LDA maybe. And then that's the most acidic position. And then after decontamination, you can use the carbon -2 tag. Oh, sorry. I saw you talking about GW4. Oh, that's the one. Sorry.
Oh, we're not. Where did you want?
I was thinking about the bottom.
This one. Okay, save that thought. So Cheng, why don't you keep thinking about this one and get ready because I'm going to ask you this one in just a second. Okay? And then in the meantime, Jess is going to help us with this one. Just go to the board over there and just pick one. Can't use the diketone. Sorry. We're not making it a imidazole. That's a good one, though. If we had the diketone here, you could use acetaldehyde, ammonia, heat, and you would get the corresponding imidazole. That would be good for that. You did say ketone before, right? Just remove the di part.
Okay.
So where does the ketone go? Okay, great. You'll form the imine. It will then do Robinson-Gabriel and cyclize close. If you make the opposite arrangement, you'll get the opposite rejoice. Questions? Okay, how about this process cycling mimic, which Cheng has already figured out for us? So just tell us what the answer is.
Okay, for the left part of the molecule,
Yep.
you can imagine it's symmetrical substitute. So maybe start with 1,2-dicarbonyl, and then that will lead you to
1,2-dicarbonyl, but we're not making an imidazole. So I see. Is your idea here that you're going to take and heat that thing up? Is that the idea?
well, kind of.
I haven't seen that way of making oxisols. Normally, that the diketone strategy you're going to want to save for imidazoles. Because the amide is a pretty terrible nucleophile. It's not really good at doing that.
I just start with Sylvie doing amino hydroxylation and then add down to a similar liking file.
Saul has dropped down the osmium gauntlet. Okay, so, and I assume you're going through azolidine.
That's exactly what I'm doing. I guess gasoline.
And so Saul wants to take that styrene, do an amino hydroxylation. How in the world do you control the regiochemistry there? Just play with ligands?
Oh, this actually isn't what I was saying at all.
Oh, good. I heard amino hydroxylation, and okay.
The amino hydroxylation I was talking about was just across unsubstituted stilbene to build the oxisol on the left of the final product.
Oh, okay.
So I like Chung's building block for the right side.
Okay, and couple this with some sort of acid, and then oxidize up. Okay, and that comes from stilbene. That looks pretty good. You can make it through a non-osmium route. Great. This is not what they did. They actually used a Van Leusen type disconnection, but not in the way you may think. Okay, so that's your starting material. We're going to couple this with AR acid and a peptide dehydrating reagent. So this is a super acidic position, as you can imagine. And so it's kind of like a malonate. If you activate this acid, it's going to add in, and then the oxygen that you get will simply cyclize on the isocyanide. So all we need to do now is come up with the synthesis of that. And you can imagine this comes from that kind of precursor. You know what would also give you the same exact product? Is 1,3 or 1,4 dicarbonyl logic. 1, 2, 3, 4. Treat this with ammonia, and you get out the product. So either the alpha hydroxy ketone is fine, or this intermediate that Sol drew, followed by oxidation. What they ended up doing was just taking the alpha hydroxy, because this is just benzoin, right? You can buy that, make the ester, cyclize to here, remove the CBZ. How do you make an isonitrile? We covered that already. Make the formamide, dehydrate, and then just treat this with a peptide coupling agent, dehydrate, cyclize, and you're done.
So if you treat that 1,4 dicarbonyl with ammonia, why do you get the product and not...
Hydrolysis?
Well, not hydrolysis, but wouldn't you get the wrong... Like, you'd have one carbon between the two nitrogens, not two. Unless I'm missing something.
One carbon between the nitrogens. So you'll make the imine here, it then cyclizes, and you get out, I think my carbon count is correct, 1, 2.
Oh, never mind. Yeah, I understand. Okay.
Luckily, we have no regiochemistry to worry about. They're both the same. Good question. Other questions? Okay. Here's a rather weird way of making an oxisol, and it speaks to a mechanism which we teased, I think, many lectures ago. So if you look at the front page of the handout, martafragin A, interesting natural product that can be derived from a tryptophan building block simply by treating with something. So what might be the reagent to convert this into the natural product? DDQ sounds pretty good. Sol has some experience with that reagent. And that goes via the intermediacy of some sort of oxidized species. Which looks something like that. You can imagine once you make this quinomethide looking thing, you would add in there. How does that work? Everybody know how DDQ works? Anybody know how? Sal probably knows how that works, but maybe someone else can help us. Sorry?
It takes hydride. Right?
It takes hydride really well. So people think this thing forms some sort of charge transfer complex, sits right on top. And then when you want to draw your arrows, and then you get the quinone product. Great.
Do you have a sense of how you control these benzoic oxidations? Because the conditions for indole benzoic oxidation seem identical to indolene to indole. And yet, like,
Same mechanism.
right.
Oh, but why does it stop?
Why does it stop sometimes and like it doesn't take any more forcing conditions, it looks like, to go here?
Well, if you took an indoline, let's say if you took tryptophan indoline and you cooked it up with DDQ long enough, you would get hydroxylation there. It is structure dependent. So when you make the charge transfer complex, if those, if it's just this system here and you treat that with DDQ, the indoline will form the indole pretty quickly before you get benzoic hydroxylation. But in the system you have with the crazy macrocycle, it probably is a geometrical reason why the hydride transfer doesn't happen. But that's why you can use a much weaker oxidant to go indoline to indole. It's an easier hydride transfer to take place because it's just like an aniline. There are some miscellaneous routes to oxisols that you see here. These are rarely employed because they often involve reactive intermediates that are things like nitrile ilids. As you see here, you've got carbines. For example, if you take this diazo compound in the presence of copper, let's say, you'll make that oxisol. You can use nitrines with alkynes and olefins, and nitrines, alpha-2-carbonyl, plus a acid chloride will also give you the product. I have yet to see anybody in medchem use these methods. But if I don't show them to you, then years from now, you'll send me hate mail. So they exist in the literature. There's hundreds of papers in this topic. You still see them coming up every day in Orglat, a variation on that theme. So it's there for the sake of being complete. Problem of the day number 4 is a typical consulting question. And asks the question, I get this all the time. People have got an acid in their hands and they say, we want 10 different heterocycles from that acid. All I'm asking from you today is simply to give me a couple of ways of going from that simple acid to the oxisol. So maybe Elena can give us one. What do you want me to do?
You can do an amide coupling and make the one for diazonium.
For example, that. Cyclize and then oxidize. Or, if you want to build in your oxidation state, maybe take that amine. Cyclize that way. Perfect. If we want to use the disconnection that someone tried to use earlier, you can also take the corresponding amide, and pretty forcing conditions will get you to product. Using PPA and heat, you can take the carbonate and turn it into the corresponding oxisol. Any other sneaky ways of putting this together? There's one other one that's not very intuitive. What do you say, Cheng?
Can use alkyne.
Use an alkyne. Plus the amide?
Or put put the amino group in the alkyne and then on this. And then
Oh, I see. Make something like this and do an amide bond formation?
Yeah.
Yeah, those are not too stable. You need to have some sort of protecting group on the amino alkyne. But I like the way you're thinking. An equivalent to what Cheng just said would be to make this. So you can make the azole triazole. It's kind of what you want. Heat that up or shine light on it, and it will isomerize, lose nitrogen, and give you the oxisol. That's kind of what you wanted. Okay, great. Before we get to thiazoles, however, we need to take a brief discussion on GW475151. So the first disconnection you may say when you look at this as well, this just looks like an SN2 reaction. So let's draw that out. And the next disconnection you may say is, well, that looks like some sort of oxidation event that took place. And this looks a lot like there's an amino acid built in there, isn't there? And that's probably why they're going to start with that, because it's super easy to buy that amino acid. Okay, let's just look for the serine and put it in there. Okay, now what building block do I use, Max, to stitch this to this? The hint is somewhere around here.
Oh, just like the nitrile. Yeah.
That will give it to you. Now, the sort of brilliant insight of the process chemist who worked on this is that they didn't want to do this oxidation at the end. On large scale, doing oxidations they're a real pain. You normally want to avoid them. Even something as simple and trivial as an alcohol oxidation on process scale, it's to be avoided. So the brilliant thing they did is they just used dichloroacetonitrile, made the imine oil chloride, reacted that with serine to give this, simply treat that with base, followed by isomerization, gives the product. So you buy your oxidation from a commercial material. You can do the same exact thing using cysteine instead of serine to make a thiazole. Okay, before we move on to thiazoles, just take a look at diazonamide. If you turn the page here, these are some various ways that the Nicolau group made the key oxisol ring systems found in diazonamide. If you look here, we see a standard Robinson-Gabriel using the Burgess reagent, followed by an oxidation, so 59 to 60. So as I mentioned here, the Robinson-Gabriel can be done with simple acid, or it can be done with whatever your favorite dehydrating agent is. It can be Tazo chloride, can be Burgess, can be T3P, PPA, all of those things will work. In this case, they use Burgess. Here's another example in rather dramatic fashion. Near the end of the synthesis, again, another Robinson-Gabriel could be used. If you're not tired of Robinson-Gabriels, here's another one. 76 to 77 is a DDQ oxidation we learned already. Following that, 77 to 78, it's another Robinson-Gabriel. And then finally, 98 to 43, another one. So there's diazonamide. Luckily, you haven't had to draw anything. But all the oxisols in diazonamide made through Robinson-Gabriel chemistry. Great. The other thing on the front page of your handout that you may want to look at is, and not have to draw, is this diabolical-looking molecule called tantazole, a tantalizing structure that has no less than 5 different azoles built into it. 4 of them are diazolene ring systems. And the beauty of the Fukuyama approach to the diazolines is a stepwise cassette-like approach where each one of these thiazolines were built one by starting with building blocks like that. So these building blocks were treated with terbutoxide, and terbutoxide is going to deprotonate something. Nick, what's going to deprotonate? There's not many options for you.
Well, it's right at the carbon. On the ring.
There's nothing on the ring.
So next to the ester.
Okay. And then this thiolate, surprisingly, will add in right there on the beta-lactone. Which, after treatment with TFA, gives you your next thiazoline. Take a look at the front page of the handout. So you build up, this is the isopropyl one I just showed you on the board. We just formed this one after treatment with TFA. And guess what? We can do the same exact thing again and again, and then finally terminate with an oxisol construction. It's a quite incredible paper. We used to spend a lot of time on this in heterocycles, but it led to extensive yawning, even more than we see now. And the problem is everybody was handicapped because they didn't know how to make benzo-fused systems. So let's take a little detour into benzo-fused systems and very quickly go through these, just so everyone knows how to make them. They're actually pretty straightforward. Normally, as you can imagine, if you want to make a benzimidazole, benzoxazole, or benzthiazole, you're going to need a substituent in a 1,2-disubstituted aromatic. So you can draw these all out one by one. But the cyclizations are pretty intuitive. Now, how do you make these things? Well, you have a variety of options at your disposal. I mean, these can be obviously made through nitrochemistry. So you have the nitrochloro, and then the nitrochloro can be displaced with something to give you your X placeholder. Some people use dinitration. If you can get lucky, you have the ortho dinitro, and then reduce it down. But normally, the way you're going to see these made is through nitrochlorochemistry, SNAR, followed by deprotect, reduce, and get your product. Now, the sort of newer ways of making these involve Ullmann, Goldberg, Buchwald-Hartwig type chemistry, where you have an ortho-halo. So these precursors, which are, you love them already from your Larac obsession. And so these can be made from the corresponding aniline and then cyclized using, pick your favorite catalyst. Copper seems to be the best for these types of cyclizations, but palladium is also known. And that's it. That's pretty much 99% of the way you're going to make benzo-fused 1,3-azoles. We should probably cover really quick tafamidis, because it's probably what's keeping Scripps alive. Just approved the other day for another indication. I don't know if you read that in the news. Cardiomyopathy for a protein misfolding disorder. And they estimated it'll be $1 billion drug from Jeff Kelly's lab. And so, as you might imagine, dump, stir, or mide bond formation, treat it with acid, and put a bucket under the hood to collect the money. I'm not sure if that's how it happened in their lab, but I think there was a lot more deep study that involved. But yeah, okay, great. How about this pyrimidine from Hennen? Now, I'm going to move rather briskly because we've seen this type of ring system yesterday, the triazine. And keep in mind that our retrosynthetic disconnection here is going to be guided solely by starting material availability. And so we know we want to use some sort of sugar. We're at the glycosidic position, and so we know we probably want to put a carbon there. It also doesn't make much sense to start off with a triazine, aminotriazine, because that's going to be highly energetic. And so when we see this, we probably just want to say, you know, that could probably be made through some sort of von Richter type cyclization. So if we go back one step, we're just going to abbreviate by putting sugar there. Treating that with sodium nitrate, HCl, will give us kind of like a von Richter cinnaline synthesis. Will give us the triazine product. And we already know how to make these. You know, you may say, hey, that looks like a nitrile that's waiting to be attacked. And you would certainly be right. All right, so you take this one and you mix it with that, and as you can imagine, a displacement takes place. Sulfur then comes back on the nitrile, and you get your product. Where does sugar cyanide come from? Well, we know how to make this already. We learned it all the way back over there. Sugar cyanide just comes from a TMS cyanide on the glycosyl, on the ribose starting material. Easy. So what looks like a really challenging pyrimidine to make, pretty easy to put together. We already covered this one, Cook-Heilbronn synthesis, when Saul asked about that question earlier. And for time constraints, thiostreptin is probably one you're going to have to review yourself. So let's skip ahead before we get to dasatinib to problem of the day number 5. So we're asking for a couple of routes here. And now that you've had ample time to think about this, maybe Ziki can help us out.
Once we separate the oxisol in the last step, for the amino bond.
So So we're going to do standard oxazole synthesis at the very end. Correct? Is that what you want, Ziki? And then all we need is a way to make that.
The selectivity is probably
How do we get selectivity between the R's and the two spots? What's a sneaky way to do it? Reminder, here's your flow chart for benzimidazole synthesis. So it's very easy to program the regiochemistry of benzimidazole synthesis just by programming the location of where you do your SNAR reaction. You happy with that, Ziggy? She looks happy. Okay, good. Problem with this on process scale is this is murderous conditions. Ethylene glycol, xylenes, like diphenyl ether bath, 250 degrees, fine for medchem. But they don't want to do this in process. And no matter what they try, they can't get the temperature too far lower than that. So they do something rather dramatic, which you guys will like. It's a cross-coupling. They break that bond. And they take advantage of what is probably, at this point, it didn't used to be this way, but at this point in 2019, there are hundreds and hundreds of papers on this topic. Of fused copper and palladium, I think it's 80 degrees, and triphenylphosphine. They get direct arylation. Is it CH activation? I don't think so. I would just call it a direct Heck reaction, but whatever. You'll see papers that are titled all sorts of things. That's a very active position, so it's very easy to metallate here and perhaps put an organocopper there. And of course, you can do oxidative addition into that AR-BR bond, as you learn in Kiri's class. So Kiri can talk to you all about the mechanism of that reaction. I look at it and I say, direct Heck. And when you see an oxazole, a benzoxazole, or even a regular oxazole, if you go and search right now, or you may have already seen it, you'll find 150 papers in a Google Scholar search on this transformation right here. Arylation of oxazoles is slim pickings. Everybody can do it. This OPRD paper, the sort of take-home message here, very similar like structure, is after the SNAR reaction. So you can do an SNAR in the nitrochloro compound. When you treat this with an aldehyde, whether it is formaldehyde or it is some R-aldehyde, you could, of course, first reduce all the way to the diamine and then add in. But the key advance in this paper is on process scale, if you just use NaS2O4, you can use the innate reactivity of the nitro, go to a lower oxidized form of the nitro, it cyclizes partially and then continues to reduce. So they call it a reductive type cyclization. Now, for the purposes of this class, just remembering that you can make the diamine and cyclize an aldehyde is fine. But when they scale this up, this is a much better way to do it than independently making the diamine and condensing that with the aldehyde. And in the final 1 minute, we have dasatinib. So dasatinib is it's a kinase inhibitor. Sorry. But it has in it, embedded in it, a couple of heterocycles that are quite important. We talked about pyrimidine yesterday, and it's pretty obvious that we can disconnect this right away to give us this compound, which we already know how to make, straight out of the lecture notes from yesterday. Of course, you can buy it, but you can also make it very easily, just from dimethylmalonate and an amidine, remember? So we need that other building block. We need the aminothiazole. Now, the faster someone gives me a building block to get that aminothiazole, the faster we can depart and conclude this marathon week of 3 lectures. So Saul is going to delay our departure. I'm extrapolating what you might mean. Is that what you might mean?
Sure.
And what do you want to treat that with to get to the product?
Yeah, I guess thiourea is no good.
Thiourea is good for something else. So if you take that simple starting material and you treat it with NBS, the product you get in situ we've got our 1-carbon radio-labeled unit. When you make a thiazole, as we would have seen here when we do thiostreptin, no time for it, but the lesson is the same. The sulfur will add on at that position where the halide is. Subsequent cyclization onto that quasi-aldehyde, hiding, gives us our product. And then methyl ester converts into amide. SNAR, done. Super. All right, folks, next week, lecture 14 and 15 and 16, 1,2-azoles will start us off. Have a good weekend.
We will send out